Okay. Now, give me a few seconds in order to change. This will be used later. So first of all, let me arrange the screens. So I have only one screen and we have to play with several windows. So in this virtual machine, I have installed the EnerVista software. Okay. So what I'm going to do is to use manual control that give me the possibility to play with the currents. Is in here. Okay. So I'm going to connect the software. Okay. And I'm going to use the, okay, I have to move in a second screen, otherwise this will not give me the possibility to do this. Okay. So here I will write the current that I'm going to generate with the DRTS, and here I will see the current I'm measuring. Okay, so settings. I'm going to looking for actual values here. So here we will see the current. This is a way for me to prove that I'm really generating current into the relay. So this is a real example. This is a live example. It's not a simulation, but everything is real. Okay, now I have to see the differential current. It is this one. Okay. Now, the vector group, I have also to check the vector group, because the vector group will define what metrics the relay is using to compensate the current is measuring. Okay, so you have to go to here. So you have to go to settings, system, setup, transformer, and windings. Okay, so we can see that is a Y. Okay, we read just once and then we will not see anymore. So is a Y delta vector group. The Y side is connected to the ground. The secondary side is not connected to the ground, and this is a YND11. This minus 330 means 11. So YND11. Okay, so if I generate one current in the high voltage side, okay, you can see here that I'm generating only one current in the high voltage side, and this brings to two differential current. You can see phase A has a value and phase C has the same value but with opposite direction. Phase B is 0. So this is exactly the this is the same example that we discussed before with the mathematical calculation. So we can also change the phase and see what happens if I'm doing here. Okay, so you see here the effect of the phase rotation. Now only A and B elements are stimulated. Okay, if I'm doing the injection in one of the phases of the secondary side, and remember, this is a delta side, and for General Electric protection, this is a reference winding, and in particular, the reference winding is multiplied by the unit matrix. That's why if I generate one current, I see only one differential current. I repeat once again, because for all the currents generated into the low voltage side, the matrix used is the unit matrix. Okay, but going back to the current into the high voltage side, where is present the compensation, I want to prove that there is the possibility into the relay to disable this compensation. So when you do the test, you have also to take in consideration the possibility that all these compensation are not enabled. So all this explanation will be useless. Okay, and this magic parameter is this one. Yeah. So settings, system setup, transformer, general. The parameter is phase compensation internal. So internal means the relay is applying the compensation. If I change this, I'm doing phase compensation external. In the next slides will be more clear what does it mean, but at the moment for you must be enough that this disable all the compensations. Okay, fantastic. Only one differential current, because now no compensation are applied. Now I go back to here. Okay, so please pay attention to this. Okay, now we will discuss a little bit more in the slides. So we leave for the moment the testing setup, and we continue with few more concepts. Okay, the differential characteristic has the differential current on the vertical axis and the bias current on the horizontal axis. So what is the differential current is clear. The bias current does not have a unique formula. There are several possible formulas. These are some examples. In case of General Electric T60, the formula is this. So the bias current is the maximum between the high voltage and the low voltage current. So the no trip area and trip area are clear. Don't need for me to explain more. Unrestrained area is where the relay trips in any case. So regardless the value of the bias current, it will trip. And there is also a the forbidden area. Okay, this is not a name that you will find in the web. Is a name that I decided. Forbidden, why? Because it's not possible to calculate values here. An easy demonstration is this one. If you try to simulate a condition where the differential current is different than 0, but the bias current is equal to 0, this is simply not possible. Okay, maybe this is I mean, this is with this formula is possible because the maximum between 0 and 0 is a 0. So this is possible. But if I change formula, and for example, I use this one, that is the sum of the magnitudes, it's not possible to have differential current greater than 0 and the bias current equal to 0. Because in order to be the differential current different than 0, must be that at least one of the two is different than 0. And if one of the two is different than 0, then for sure this sum cannot be 0. So regardless of the specific example, you have to be aware about the fact that there is an area here that has points where you cannot calculate the currents. There is another element, protection that typically is used, but the so-called harmonic restraint. So there are harmonics that can be blocked. In particular, the second harmonic appears when you have inrush current, so when you energize the power transformer. If you don't compensate the inrush current, this will make in the position to open the breaker every time you try to close, because you close the breaker, the magnetizing current start flowing. This is measured by the relay. This will produce a differential current different than 0, and this will make the relay tripping. So you try to close and the relay will open again. So you need to apply a filter. You need to block the protection, the differential protection, if the percentage of the second harmonic is too high. That's why the harmonic characteristic has this shape. So if the differential current is high enough for the relay to trip, but the harmonic content is high enough, in particular more than the threshold, then the trip will be blocked. This waveform is a screenshot taken by the software. So if you want to test the harmonic restraint, you can simulate points here, and this is the waveform. So you can see that there is a small percentage of second harmonic superimposed on the 50 Hz. In case of fifth harmonic, the concept is the same, but the waveform will be with this shape. I forgot to mention that you can ask questions. You can ask questions in the dashboard. I see there are already several questions here. I will answer to all of them in the end of the session. So please write your questions. You will get an answer in the end. Now, let's go a little bit deeper inside the General Electric T60. Let's start from the magnitude compensation. So the question is, how General Electric T60 calculate the magnitude compensation factors? If you look in the user manual, you will find basically an algorithm. So it's not a simple formula. You have to understand this logic. So and the end value of these compensation factors also depends on this parameter. It's called a reference winding selection, but please don't be confused by the name. This reference winding is not for the phase compensation. For the phase compensation, you have to consider this one, where it's written phase compensation. This reference windings is only for the magnitude compensation. I know it's confusing, but try to read this 10 times and keep this well in mind in order not to be confused in future. Okay, so if if you change this parameter, and if you follow this logic, you are able in the end to calculate what are the magnitude compensation factor that are in the end these two. Okay, so this is something we have seen before. According to this parameter, if it is set to internal, the phase compensation is done with matrices, and the reference winding follow this logic. If you have a YY vector group, then the reference winding is the high voltage side. If you have Y, delta, or Z, then the reference winding is the low voltage side. Okay, so if there is a delta or a Z side, it will be the reference winding. In case you have double delta, double Z, or delta Z, Z delta, then the reference winding is the high voltage side. Okay, so this is also explained in the user manual, but I would like to write this table for you to help to understand better the behavior of the relay. In case this phase compensation is set to external, then the phase currents are not multiplied. So this is true, and you have seen before with a real example. But when you how can you decide if this parameter must be set to internal or to external? External is when in the plant are present external CTs for this compensation. Another way to call these external CTs are interposing CTs. A reason to have interposing transformer can be the following. The plant is quite old, so you want to replace an old differential protection, an electromechanical differential protection, with a new one. But you don't want to modify the wirings and all the current transformers in the plant. So you don't want to touch anything else than the relay. Since all the electromechanical relays were not able to make this kind of calculation, then all this compensation had to be done with CTs, external CTs. So trying to explain this concept in short. So the primary current are like this with a phase shift. Then you have current transformers, but if I don't compensate this phase shift, this will not be able to see differential current equal to 0 when the parent transformer is in service. Okay, so if I'm not playing with the secondary side connection of these CTs, the same phase shift of the primary current will be the same at the secondary side. So putting in series an interposing transformer with a specific delta connection of the secondary side, then you are applying a phase rotation. Okay, so this is the reason why it exists, that parameter, to exclude the automatic calculation. Okay, so also the zero sequence compensation is obtained, because remember, in delta connections, the zero sequence simply does not exist. Okay, finally, we are in the end of the presentation. This is a template that you can find in TDMS Pro that is giving you the possibility to input the parameter that you can find in the relay. So it's enough that you open NRVista, you look for the right parameters, then you set into the template, and all the calculations, all the complex calculation that now you know that must be taken into account are automatically performed by the software. So you will see in a few minutes how easy is the test of this differential protection once you have a template and you know all the concepts that we discussed together. Okay, so now we go directly to make some real testing. Okay, this is an example of where to find the parameters and where to copy into the template, but let's doing it now. Okay, so let's go into the transformer differential software. Okay, so this is the testing window. You will find here the side of the fault that you want to generate, the fault type, but we will see later. Okay, this is the differential characteristic that is not the one is present into the relay. So we must modify these parameters in order to match the parameters present in the relay. Okay. I need to go to setup, click on relay settings, press on. Sorry, I'm not sure if I'm doing this now. I can keep in the same screen. No, just 1 second. I need to move this here. Then I have to do this like this. Okay, now I can click on both. Okay, so let's keep only what we need. We don't need this, but we need this. Okay, so let's start. Okay, we can set the power, so 250 megavolt amp, 400 kV, it's this. Okay, connection is Y, so star. The grounding is within zone, so it is grounded. Then we do the same on the secondary side. Okay, 250 megavolt amp. No, M, capital M. Mega is a delta. No, sorry, I'm not doing it in the proper template. I have to do new. I have to choose a specific model. Okay, the GET60 is a multifunction relay, but I want to activate the differential element. Okay, this is the template for GET60, sorry. So I have to repeat the settings here. 400K, star, grounded, then low voltage, 250 mega, 66 kilo, delta, isolated. Okay, what is missing? I have to set the turn ratio of the current transformer. I have to look for here. AC input current. Okay. Okay, the primary side has 160 and the secondary side has 400. Okay, so 160. And low voltage side is 400. Okay. Now I have to set the differential characteristic value, and also I have to look for that. Differential characteristic. Okay, this one. Okay, pickup current is 0.15. Slope 1, 33. Slope 2, 80. 80. Break 1, 1.5. Break 2, 7. Then we can set the values of percentage. Okay, in rush level is the second harmonic, so 20. And the fifth is 10. Okay. Last but not least, we have to be sure that the phase compensation is set to internal. So I'm saying that this is internal, so same like this, and this is automatic selection like this. Okay, very well. Now, if I press exit, these settings will be sent to the differential module, and now I have the characteristic here with the proper shape. Can do some zooms. Okay, so now we can do some tests in order to see that every point in this plane will generate the differential current exactly according to the values in this plane, because it's important to verify before to start any test that the relay is measuring correctly all the currents. Okay, so I want to to close all of this and see only the differential current values. Okay. No. Okay. Okay, so I connect. No, before I have to disconnect the other module. Sorry, but my screen is full of windows and I have to. Okay, connect. Now, I want to generate a value. For example, let me increase the time here. Then, for example, I want to generate this point, 4 as a bias current and 1 as a differential current. So what I expect is to see this, exactly this number, so 4 and 1 here. Okay, it's not 4 and 1. Maybe I did some mistake somewhere. Let me check once again. Relay settings. Okay, so this is quite normal when you do live testing. So I've already did a mistake in setting. Okay, in order to be more fast, let me open a setting file that I saved before, because probably I did a mistake. Okay, so add and start. Yes, now it's correct. You can see 4 as a restraint current and 1 as a differential current. The same must happen even if I change the side. Okay, this new graph is the so-called virtual characteristic, and the reason why it exists is explained before, has been explained before. So add the test and start. So 1 and 4 will be for phase A. The other two will have different values. In particular, if I do it once again, the differential current of the phase A is the double of the differential current of the other two phases. Okay. So let me do the same exercise again, changing, for example, the phase. So you will see that now two other elements are stimulated. So this is just to say it once again, but this is a very important aspect. I really recommend you to spend time to understand if the differential current that you want to generate is correctly measured by the relay. Otherwise, you can't be sure about what you are doing. Maybe you expect the relay is tripping or is not tripping, you expect something, and then you are lost because you don't know why this strange behavior is happening. But if you are sure about the measurement, then you can safely perform all the tests. So just last example like this, I try to input strange values, for example, this one. So 5.7, 2.1, add the test, start. You can see exactly this value. We can do the same with harmonics, because here you measure the percentage of harmonics. So it's enough here to come to this part, then fixed values. Let's say that I want to do, say 25%. Maybe a little bit more of differential current, say 3 or 4. Add the test and start. You can see 25% of second harmonic. Okay, so also the harmonic is measured correctly. So again, change to fifth, add the test, and start. Okay, so the 25% on the fifth harmonics. Very well. Now we are sure about the connections and the settings. We can perform some tests and understand also how to use this software tool. Okay, we have the characteristic here, and this is the table with results. So let me restart from the beginning. We have a nice way to do quick test, the so-called click and test. So let me reduce down to 0.5 and say 0.2. Okay. Click and test give you the possibility to click on the point and the proper current are generated. And here you have an immediate evaluation about the result. So if we click above this line and the relay trips, is a pass. Same if I click below the line, this must be a timeout. Okay, if I want to see the time that has been measured is here. So here I expect that is tripping. And here I expect that is not tripping. Okay, so these are a lot of columns. You can see also the current and the angles, all the 6 currents that are generated. But if I want to change this column layout, is enough that I change. So for example, if I don't want all of this, I can do this. I can just keep what I need. So side, nominal current, differential current, and nominal restraint current times no results, the measured time, and for me can be enough. Okay, I can do also testing on the low voltage side. Okay, so everything is working very well. Now, if the result is not okay, this will become red. Okay, now I intentionally disconnect the trip contact. I click here. So the trip will not be measured by the RTS. You will see a timeout here. That's why you have a red. Now I connect again the trip contact. I ask to repeat the test. Okay. Now I want to be more precise. You can see this area that is the part that is changing between one side and another. Okay, and I can go very close here just to see that this is really the characteristic. Okay, but there is a smarter way to perform the characteristic verification, and is the following. We can do verify characteristic. So we can decide from what point, from what value to start, what value to stop. For example, we can add points. You can see this cross. You can also put more tests. So if I reduce the step, okay. So I will not add all this step because otherwise it will take too much. So let me reduce to, okay, only a few points. Add and start. So the algorithm now is testing around the border, and in the end, if the border is in the position that we expect, we will get a pass indication. Okay, so okay, the test is finished. So I think we dedicate enough time to this. I hope the concept explained are clear enough. I repeat again, these concepts are not easy, in particular if it's the first time that you see all this complexity. Don't be scared, but what I can guarantee is that all the concepts that are described in this presentation are important. So if you spend time in understanding this, for sure they will be useful. And not only for the General Electric relays. These concepts are valid for all the brands. Can be a Siemens, can be an ABB, can be a Schneider, everyone. Because the concept that these relays must use must be the same, because they are protecting the same object that is a power transformer. So for sure they must have the same approach to this. Okay, these are my references. This is my email, my phone number, and my LinkedIn profile. So if you have questions, you want to understand better something, feel free to send me an email. For me, it will be a pleasure to answer.